Hello everyone, welcome to the next MCAT ACE lecture, and in today's lecture we are going to be talking about solutions and solubility. So let's go ahead and get started. As a general outline, this is what we want to cover in today's topics. So we're first going to briefly define solutions, which includes solvent and solute, and an understanding of concentration. And then once we discuss concentration, we want to look at the different types of concentration. So the most common one would be molarity. And then we also have things such as part per million or part per billion, and then solutions that are based solely on weight or volume. And then we'll also look at dilutions and KSP, which is the solubility product constant. This relates back to the equilibrium work that we've been going over. And then finally, we will have our usual practice session. So let's look at some of this material. So for solutions, when you hear the term solution or somebody's talking about it, we are talking about two major components that are making up a solution. Now the first one is the solute, and that's the chemical compound that is going to be dissolved in a solvent. And then you also have a solvent, and that would be the liquid that is doing the dissolving. So that's the liquid that's used to dissolve all the solutes that you would put in. And when you combine them together, you will get a solution. Now, typically solutions are homogeneous in their composition. So it's not to say that you can't have a heterogeneous type of makeup, but usually that's referred to as a mixture more than it is a solution. So an example would be salt water. So if you were to take basic sodium chloride like table salt and you were to dump it in water in order to make salt water or saline, then that would be an example of a solution. With the sodium chloride, and you can see this in red here, the sodium chloride, right, would be the solute, and then the water would be the solvent. Now, it is very common to come across water as a solvent, which we would call an aqueous solution. However, other organic solvents can certainly act as the solvents, such as methanol or acetone or acetonitrile. Any liquid is capable of being the solvent as long as it has some capacity to dissolve the solute. And that goes back to the general like dissolves like principle when you're trying to pick out a good solvent. So what about the term saturation? Because sometimes you can come across unsaturated, saturated. So what do these terms mean? Well, if a solution is considered unsaturated, that means that it still has more capacity to dissolve solute. You could still dissolve some more of the solute in the solvent. If it's saturated, it means that it's going to contain the maximum dissolvable amount of solute possible. So any excess solids are going to sit and stay at the bottom of the container. They're not really going to be able to dissolve into solution. And then when you have supersaturated, that is a situation where it contains slightly more than the maximum solute, and then the solute could easily be precipitated out of solution. So a lot of people will get confused at first and think, what do you mean supersaturated? You can't go over saturated. Well, solubility is a property that can be manipulated by the temperature that the solution is currently at. So as you increase your temperature, you increase the solubility or the capacity to start solubilizing solute. And what you can do is you can heat a solvent up to close to boiling or at boiling, add excess solute that would dissolve at a higher temperature, and then you have to slowly let that solution cool. And as it cools, the solubility comes down, but that solute is still dissolved in there. Now, these situations where you have something that's basically supersaturated are going to be very, very sensitive to things such as bumping or shock, because it will very easily precipitate the crystals back out of solution. You can also add what's called a seed crystal. And when you add a seed crystal, you put one crystal in, and that one crystal will shift the equilibrium enough that all of a sudden a lot of the other crystals will collapse out of solution. It will come back to a saturated state, and all of the excess will be removed. All right, so a basic overview of concentration. Concentration is defined as the mass of solute per per the amount of solvent volume. Now, we said at the beginning when we were looking at this outline, there are a lot of different ways that we can define concentration in terms of units. So the top portion, whenever we're looking at our ratio, will always deal with the solute, and the denominator, or the bottom portion, will always deal with the solvent. Some common solute units that you would come across would be moles, particularly in molarity, grams, and milligrams. And then common solvent units can include liters, milliliters, and centimeters cubed, because those are typical volumes. That is also, you could have, with the solvents, you could have mass. So sometimes you will see, for instance, a weight by weight solution. Usually if it's a liquid, it tends to be by volume, but sometimes it will still be by mass, and that is possible. When you do it by mass, it can be important to know the density of the given solvent that you're using. Again, if it's water, most people usually assume just the 1 gram per milliliter. Now, types of concentration. So now we're going to talk about the specific units and the types that would be included here. So we have molarity, and for molarity, you've got moles of solute per liters of solvent, and we're going to go over a general example for all of these. For the part per, meaning part per million or billion, the concentration is a ratio out of 10 to the 6 if it's part per million, or 10 to the 9th if it's part per billion. Now, the 10 to the 6th and 10 to the 9th, if you take that out and you were to use it as an exponential multiplier, 10 to the 6th comes out to a million, and 10 to the 9th comes out to part per billion. So to give you a general example, all right, if you have grams, going to milligrams would be a 10 to the 3rd, and then going to micrograms would be 10 to the 6th. So if you were to report something as micrograms per gram of material, that would be an example of a ppm. That would be a part per million, because the difference between units is 10 to the 6th, and therefore that's how many parts per million you have of whatever type of material you're looking at. So then if you go to this next one down here, you can see the W by W, WV, VV, that's weight and volume. So this is usually reported as a percent, so it can be weight by weight percent, weight by volume percent, and volume by volume percent. So this is a calculation of concentration using weight or volume, or sometimes a mixture of both. And remember, as I said a minute ago, the numerator will always be the solute, and the denominator will always reference the solvent, whether you're using mass or volume in these cases. So molarity. Molarity is, in my opinion, the most common type of concentration, particularly if you're working in a chemistry lab or you are around chemists. Now, in day-to-day, everyday life, it might be something more like, grams per milliliter or something like that. But molarity is very common inside of a research lab or a chemistry setting. So, what is the molarity of a saline solution in which 75 grams of sodium chloride is dissolved in 500 milliliters of water? So the way that you would set this up is your molarity is going to be moles of the solute over liters of the solvent. So take a look at what I have here. This is 75 grams, which comes from the problem, divided by 58.44 grams per mole. So that is the molar mass of sodium chloride. So that would give me the moles of sodium chloride if I took the mass divided by the molar mass. And then down here, if you notice, it says 500 milliliters. I converted this to liters. Molarity is specific. You have to use liters as the denominator. And so I needed to move this back because a milliliter, there's 1,000 milliliters in a liter, so you have to use the 10 to the 3rd factor and bring it down to 0.5 liters. So if you were to plug all that into your calculator, 2.57 molarity is the value that you would get here. So let's take a look at a part per example, which is a part per million in this case. And again, you could apply this with a billion if you had a larger difference between the units. So a lab finds 5 milligrams of a toxin in a 150 gram sample of soil. What is the ppm level of the toxin? And then you can see the little note there. It says difference in units must be 10 to the 6, and that's because we're doing a ppm. So if it's giving me the milligrams and I have the grams, I could do one of two things. I could convert the milligrams into micrograms so that then I'm reporting micrograms and grams, or I can keep the milligrams and I can take the grams and I can turn those into kilograms, because milligram to kilogram is 10 to the 6 and microgram to gram is 10 to the 6 if you look at the difference between the units. So in this case, I went ahead and I moved the grams into kilograms and I did the ratio. So I have 5 milligrams divided by 0.150 kilograms. And if you calculate that, it comes out to 33.3 ppm. So a lot of times ppms you may see in reference to things that are particularly potent or toxic. So if you were maybe to visit something like the EPA website or something along those lines, they may report heavy metals, some other type of pesticide or toxin that might be found in the environment. They'll report it in a ppm or a ppb in terms of legal limits or safety limits or things of that nature. All right, weight by weight percent example. So this is in that bottom portion where we were looking at weight by volume, weight by weight. So we're going to do a weight by weight example here. So what is the percent concentration, weight by weight, of 500 milligrams of sodium sorbate in 500 milliliters of water? So what you want to do here is you would want a weight by weight ratio, and you should be keeping the weights the same unit. Now in this case you have more flexibility than you did with the molarity example where you had to use liters. That's the way that it's defined. Here it's weight by weight, but you want to make sure that this is a percentage that's coming out of what we would consider to be 100%. And so when you do that, you want the units to align in order for this to make sense. So I'm going to do grams here. So the 500 milligrams of the sodium sorbate is going to become 0.5 grams. And then the 500 milliliters of water, I'm making a general assumption and conversion of the 500 milliliters of water into 500 grams of water. And that's just based on the density of water around room temperature is approximately 1 gram per milliliter. So you go ahead and you look at this, and the concentration here, right, would be 0.001% weight by weight. So let's discuss dilutions now. Okay, so when you're talking about a dilution, you are taking a concentrated solution and you are making a less concentrated solution out of it. So to dilute something means essentially, and pardon the term because it's not always water, but to water something down, right? So you're essentially taking your solvent and you're increasing the amount of solvent so that there's less solute per some amount of solvent. Right? Now, a concentrated solution can be diluted to a new desired concentration using this formula right here, C1V1, C2V2. Now, you may have seen this as various forms. A lot of people will call this M1V1, M2V2. Which is molarity if you were specifically looking at that, but it can be used as any general concentration. It doesn't have to just be molarity. And you also may see this as CIVI and CFVF for initial and final concentrations. Anything of this sort, when you see concentration in volume 1 and then concentration in volume 2 being set equal to one another, this is a dilution. So what do each of these represent? Well, when you have C1 and V1, those are going to be the initial concentration and volume. And then when you have C2 and V2, those will be the new dilution values. And you could switch it around. It doesn't really matter mathematically, but that's in general what we would keep with. Now, here's what's important with this equation. Any unit may be used, but you must stay consistent in the units, okay? So that's kind of like the weight by weight that we just saw. So what does this mean? It means whatever I choose for concentration 1, that's what concentration 2 has to be. Whatever I'm going to use as my volume unit, they have to be the same. So I could use microliters, I can use nanoliters, I can use kiloliters. It doesn't really matter as long as I am keeping the units the same. So whatever unit V1 is, V2 has to be the same unit, and then whatever concentration C1 is at, the same concentration unit has to be applied to C2 in order for this to work. All right. So now let's take a look at a dilution example. Here we have a grad student needs to make 2.5 liters of 4 molarity HCl. If the stock bottle is 12 molarity HCl, how much concentrate should the student dilute? So then we take a look here. Okay, the way we would set this up is we say, all right, I'm going to use M in this case because we're talking about molarity. So M1 V1, M2 V2. So what is M1? Do we know? Yes, it is 12 molarity. Now keep in mind, M1 is the initial concentration I'm working with, all right? It does not mean the one that gets reported in the problem first. So when you see it says 4 molarity here, just because you see that first doesn't mean it gets plugged in here. You take the initial concentration, what the student has is a stock bottle at 12 molarity. This is what he wants to make, so this would be M2, right? So M1 is 12, V1 is the question. It's how much of V1 should we take and then dilute. All right, and then for this right here, M2 would be 4 molarity. That's the desired concentration. And then 2.5 liters is the amount that this graduate student would like to create. So you go ahead and you put all this together. Algebraically, you solve for V1, so you would multiply 4 times 2.5, and then you would divide by 12. And so the 10 divided by 12 is going to give you 0.833 liters. And if you wanted to convert that, you could then convert it after you get your answer into 833 milliliters. So that is how much of the 12 molarity solution the student would take. And then, once they have 833 milliliters, they would need to dilute that amount up to 2.5 liters using distilled water or deionized water in order to bring it to the final concentration. So this is the final volume, and then V1 is just the volume of concentrate that you would be taking. You then, in order to dilute that concentrate, you have to bring it up to the volume that you stated over in V2. And so that is an example of how a dilution would work. All right, now KSP, which is the solubility product constant. If I'm just going to make a note here, if you have not watched the general lecture on equilibrium yet, I would strongly encourage you to do that before starting to go through this portion of the lecture, because we are going to be reporting and using some general concepts that are established with the equilibrium constant. And so it's very important that you understand that before proceeding forward and trying to learn things like KSP or Ka or Kb for acids and bases. You need to understand just general K, which is the equilibrium constant, all right? Because these are all subsets. They're different types of equilibrium constants when you see these modifiers on them. All right, so the KSP is a value that determines the relative equilibrium between solids and their dissolving into an aqueous ion in solution. So essentially what we're looking at is you put your solid solute in and you wait for that to dissolve, right? And when it dissolves, it goes into these aqueous ion forms, or if it's in some other solvent, it's not technically aqueous, but it's ionizing in the solvent. So when this happens, and when you start dissolving, you need to realize that there's an equilibrium that exists between the solid state and the ionized state of these salts. And a typical dissolving process you can see right here would be A dissolves into B and C. Now A is solid and B and C are aqueous in this case. And the little a, little b, little c, that all represents the coefficient, right? The molar ratios that would go in front of that. That becomes very important when we deal with equilibrium constants. So you have A as the solid compound, it dissolves into B and C, and it forms those aqueous ions from A. Now, rewriting the equation up here, let's consider this. Given that the solids and liquids, okay, so in this case it would be any type of solvent, it would be water if we're dealing with aqueous, are going to drop out of equilibrium calculations. So remember, when we deal with solids and liquids in general equilibrium conditions, they get omitted from attempting to calculate the equilibrium constant. And then we do the products over reactants. So what we're left with for KSP is just B and C. It's only products. So since it's products over reactants, it would be B and C over an implied 1, because the A is going to drop out as a solid. So when we're doing this here, the KSP then becomes B raised to the coefficient of B, C raised to the molar coefficient that is small c. Okay, so this means that larger concentration of aqueous ions, the more soluble the solid. And that may seem like an obvious statement, but we're looking at it mathematically here. So what this says is, remember that B and C in brackets are concentration, molarity, right? So as the molarity of B and C increase, as these guys increase, that is saying that the solubility of the aqueous ions is going to be going up, so therefore KSP is going up. It's all about solubility. It's saying the higher these concentrations are, it means the more solid has dissolved, and therefore the more soluble that solid is in a given solvent. So, an example here. Let's consider calcium hydroxide, which is going to break apart into calcium 2+ and 2 hydroxide ions in aqueous form. So what are the concentrations of calcium 2+ and hydroxide at equilibrium if KSP for calcium hydroxide is 5.5 times 10 to the negative 6? All right, so this is giving you, in this example, the KSP and asking for the concentrations of calcium and the hydroxide ion. So what you want to do here is you want to create an equilibrium chart. So these often are abbreviated as ICE chart. So if you hear me talking about an ICE chart, the ICE chart stands for the initial concentration, the change in concentration, and then the concentration at equilibrium. This is a very common practice in undergraduate general chemistry classes, right? And then you solve for X using the KSP value. And we'll walk through one of these and take a look here. All right, so here's ICE, right? Initial, change, and equilibrium. So I wrote out the equation here again. At the initial state, we have some amount of calcium hydroxide, which we'll label as X, and we have no calcium or hydroxide as separate ions, right? So this is the moment that we start the clock and that we are looking at solid calcium hydroxide that's as soon as it's hit the water. Nothing's dissolved yet. All right. Then the change. So what's going to happen on the way to equilibrium? The change is that we're going to lose X, and we are expecting that we will gain this right here, X calcium and 2X hydroxide. Now, why do we say this? Because look, here this is combined as a solid. So for every one of these that we lose, right, we are going to expect that we gain 1 calcium, but we're going to gain 2 hydroxide, right? Because if there's an implied 1 in front of the calcium hydroxide, there's a 1 in front of the calcium here, but there's a 2 in terms of balancing in front of the hydroxide here. So if we were to look at this, we would gain 1 calcium and 2 hydroxide every time one of these calcium hydroxide molecules were to dissolve and break apart. So then at equilibrium, we would say that we have X calcium and we would have the hydroxide as 2X. Again, at equilibrium, solid, we do not consider or count. So we are not interested in adding that into the KSP equation. So what does this become? For KSP, this becomes x times 2x squared. Now where is this coming from? Calcium, so if you go back, okay, remember that we said B raised to the B and C raised to the C, right? So the B here, raised to the B, is going to be calcium, and calcium had a 1 as its coefficient, so we don't need to worry about that. And then C is going to be the hydroxide, raised to the C. So hydroxide is going to be 2x, so we put 2x down in here, raised to the 2, because that's the coefficient there, to the 2. So it's going to be x times 2x squared. That will give us the KSP. Now we know what the KSP is, so we want to set the KSP equal to this and solve for x. So we take 5.5 times 10 to the minus 6, that came from the problem, all right? And you're going to combine this, simplify it, and solve for x. So x times 2x squared becomes 4x to the third, all right? Now, when we're doing this, okay, you need to realize when you have 2x and it's being squared in brackets, that means that you are going to have 4x squared. And then you have x times 4x squared. So that's going to be 4x cubed, because remember, when you multiply x and x squared, you're going to add the coefficients together. That's the way that this works. And then you have 5.5 times 10 to the minus 6. You would need to divide that by 4. And then after you've divided by 4, you would take the cube root of that value. And I would encourage you to try along and do this on a calculator. And what you would get is 0.011 molarity. So what does this tell us? It tells us if x is 0.011, then calcium is equal to 0.011, and hydroxide is equal to 0.022, because the hydroxide is 2x, right? If we were to pull hydroxide molarity out of this bracket, it says 2x. So it's going to be 2 times this value here. And that is how you would solve for a KSP example. Right? Now, you may also be given the concentrations at equilibrium, and then you could solve for the KSP. So you can either be given the KSP, solve for concentrations, or you can be given the concentrations and find the KSP. It's all just a mathematical equation. And there's one more thing we want to mention here before heading over to practice, and that's the common ion effect. So if a common ion already exists in solution, the solubility of the corresponding solid that's going to be dissolved will be greatly reduced. And this is the Le Chatelier principle. So just going back, let's highlight this equation for a second. I have calcium hydroxide here, right? So let's say that instead of putting calcium hydroxide into pure water, I take water and I dissolve some calcium chloride in that water first. So I already have some calcium that's hanging out in solution. And then I attempt to dissolve calcium hydroxide after I've already dissolved some calcium chloride in the water. Well, because I have already started to move a lot of the calcium 2+ over into an aqueous phase, there's going to be less saturation room for the calcium of the calcium hydroxide to break apart and move over here. Because remember, when we're dealing with Le Chatelier, it's a bouncing back and forth. Okay, we were just showing this moving over into aqueous, but if this is in equilibrium, you draw the other arrow going to the left, and you would say, well, if I already have calcium here and then I'm trying to push more calcium over, it's going to shift back this way, right, to maintain equilibrium. So it's very important to understand that if you have a common ion that is going to be present in what you're attempting to dissolve already in your solution, your solvent, then you are going to greatly reduce your KSP value and your ability to solubilize that solid compound. And you can actually check the difference of this. You can find videos or things like this where you are taught how the common ion effect works, and you can actually calculate the difference between what if you were to just find the KSP, and then what is the new KSP if you account for that ion. And just to show you guys or give you a hint as to what would happen, this value would not be 0 starting out. and that's important. So that's going to affect how the rest of this would play out. All right, so with that, we will say that we're going to wrap up the actual lecture portion here at half an hour, and we will move over and do our practice questions before finally wrapping up here. All right, so here we are with the practice questions. So let's go ahead and take a look at these. You should try them on your own as usual, and then we'll walk through them together. So, number 1, an initial sample of sodium hydroxide is of an unknown molarity. If 25 milliliters of the concentrate was added to 175 milliliters of water, and the final molarity was determined to be 0.025, what was the initial sample molarity? And you can see your choices there. Number 2, a lab extracts a 5-gram sample of material in 50 milliliters of water. A 1 milliliter sample of the extract is analyzed and found to have 3 nanograms of metabolite X. Given this, what was the concentration of metabolite X in the original sample in ppm? And then finally, number 3, this one will take the longest, it'll be the most work. The solubility product, KSP, of calcium fluoride at 25 degrees Celsius is 3.9 times 10 to the 11th. Times 10 to the negative 11th. Its solubility in 1 liter of water at this temperature is 0.017 grams. What would be the solubility in grams per liter of calcium fluoride in a 0.1 molarity solution of potassium fluoride? And then you can see the atomic mass given there for calcium and fluoride. Right? And then here are the answers here. So just so you have a heads up, number 3 is exactly what we talked about at the end of the lecture, which is a common ion effect. So you're going to need to do your icebox setup in order to solve this. But when you're getting ready to do that, you need to look for the common ion and account for that in your initial state when you are starting your icebox setup. So go ahead and work through these. Pause the video if you need to write any of these down. I'll scroll through one more time slowly. And as you're working through them, see how far you can get and pause the video. And then you can unpause it and come back as usual when you're ready for the walkthrough. So I will see everybody in just a moment. All right, hopefully you had a chance to work through some of this. So we're going to go ahead and get started here with the walkthrough answers. So question number 1 here is simply a dilution question, but you have to pay attention to the numbers and what it's stating. So it's asking what was the initial sample molarity. So we can call that M1. And then how much of M1 did we take? It says here that we took 25 milliliters. So that's going to be V1, and we'll go ahead and keep it in milliliters, because remember, we can pick anything as long as the units stay equivalent. And so then if we take a look at M2, M2 would be the concentration after dilution, and then V2 would be what? So this is where you have to be careful. You have 175 here, and a lot of students might grab that because they see the second volume. But it says 25 mils of concentrate was added to 175 mils of water. So the real total here is 200 milliliters because it's total final volume of your solution. That's how you're going to find your molarity. So if you go ahead and simply algebraically rearrange this, you would divide each side by 25. And by doing that and solving what you have on the right over there, you will come to M1 equaling 0.2. And so the correct answer would be A in this case. All right. Number 2. A lab extracts the 5-gram sample of material in 50 mils of water. All right. So in this one, we've got a sample, we're extracting it, and then we're taking a subsample of that extract and we are going to analyze it, and it's found to have 3 nanograms of metabolite X. So we want to find the ppm of metabolite X in the original sample. So here's how you have to go about this. when you do your analysis in the lab, you find out that you have 3 nanograms, and that's per milliliter, right? Because it says that we analyzed 1 milliliter and there was 3 nanograms in that milliliter. So that's the concentration. Now, it was a 50 milliliter extract. So if I want to find the ppm of the original sample, I need to know how many nanograms came from the original sample. This 3 was not the total number of nanograms in the original sample. This 3 simply represents the 1 mil. Well, there was a total of 50 mils that we extracted in. So I would need to take this times 50 milliliters, right? And so if I do that, I come out to 150 nanograms. So 150 nanograms is what I have in the entire 5 gram sample, right? If I account for all 50 milliliters. So what I have to look at then is what I'm dealing with is nanograms and grams, right? So this ratio here would be 10 to the 9th, and that would be a part per billion, and we're looking for a part per million. So what I'm going to do in order to help adjust this is I'm going to turn the nanograms into micrograms. And the way that I do that, since micrograms is a 10 to the 3rd difference and it's a larger unit, I simply have to divide my nanograms by 1,000. So you divide the nanograms by 1,000 and you get the micrograms. So it would be 0.150 micrograms. Okay, now remember, this is not the ppm. The ppm is when we divide that into the total grams, and we had 5 grams total. So it's this, when you solve for this, that would be the ppm right here. Okay, and again, notice micro and then base unit, that's a difference of 10 to the 6, right? So that's a ppm. So if you solve that, you're going to end up with D as the correct answer. You should get 0.03. And the rest of these drop out. All right, now for the one that's going to involve a little bit more math here. All right, so if you read this, what we have is we have the calcium fluoride, and we know that it's going to we're going to attempt to dissolve the calcium fluoride in a solution of potassium fluoride. So the common ion here is going to be a fluoride ion, right? So we're going to be on the lookout for that when we do our icebox. Now, what we can do here is look at a little bit of process of elimination in this one. The other ones, it was easier to go straight for the math. So if we know what common ion effect does, which based on Le Chatelier's principle, if we already have the potassium fluoride in solution at any concentration and we try to dissolve calcium fluoride, right, it's going to affect the solubility. It's going to decrease it. So we're not going to get as much going into solution if we already have some fluoride over there. So let's look at A. Addition of the 0.10 potassium fluoride increases solubility of calcium fluoride. That's a no, because we would not increase. Okay. Then it says the same thing here, but decreases. This is possible. Addition of it decreases the solubility from 0.017 to 2.9. So that's also a decrease. That's a potential. And then it says the solubility of calcium fluoride in water is unaffected by the presence of added potassium fluoride. That's incorrect. That's basically saying common ion effect doesn't exist. So no, that's not correct. So we have B and C. That's good. We're down to 2 of them in process of elimination. All right, now look carefully at what this says before we start the math. Addition of the potassium fluoride decreases solubility by 2.9 times 10 to the minus 7th grams per liter, right? And then this one, because they look similar, says addition of this potassium fluoride decreases the solubility of calcium fluoride from this value to this value. So here's the key when you're looking at this, okay? When we solve for the answer, if we find that the answer comes out to be this exact value right here, then this is the correct answer. But if we see any other number, it's likely going to be this. Now, why is that the case? Because this is saying that the calcium fluoride is going from this value to this value. So if this value pops up, then that's what we're looking for. In B, it's saying that it's going to decrease by this amount, right? Well, we already have some starting point, and the starting point is 0.017. So if you took 0.017 and then subtracted this value from it, that value, if that comes out, that would be answer B. So just keep that in mind, because it's important to distinguish what the difference is here when we're talking about this. All right, so let's set this up. We're going to talk about our calcium fluoride. So we're looking at calcium fluoride, solid, and then we set up its equilibrium to calcium 2+, aqueous, and then we would generate 2 of the fluoride ions when we're breaking this apart into its ionic form, aqueous. All right. Now, what I'm going to do here is I'm going to set up my ice chart, and we'll pick out a different color and we'll start filling some of this in here. Okay. So, at the initial state, right, we're going to have nothing for the calcium. However, for the fluorine, we would have 0.10. Now, where is that coming from? That's coming from the fact that we already have the calcium fluoride is going into a solution that has 0.10 potassium fluoride, right? So this is the common ion here. It's the fact that when we start out, when we initialize, we already have some of the fluoride ion present. All right, so then the change here, we would have plus x, and here we would have plus 2x. So now, when we're at equilibrium, what do we have? Well, we would have x, and we would have 0.10 plus 2x. So it's a little more complicated than what we had in the previous example when we were looking at the calcium hydroxide. All right, so we want to set this up. Now they do mention up here the KSP value. All right, so this is going to be important because this value right here is what we're going to need in order to plug this in and solve for this. So what we'll do is we'll set the KSP value up, and we'll say 3.9 times 10 to the negative 11th is going to be equal to, and it was x, right? And then that x is going to be multiplied by the entire portion for the fluoride, which is 0.1 plus 2x squared. Now remember, it needs to be squared because you've got this coefficient up here. We don't want to forget about that. All right, so I'm actually going to remove this here because this looks a little bit too much like a coefficient. I was trying to make it a multiplication. All right, so the next thing that we want to do is simplify what's on the right-hand side of that equation. Now, in a case like this is an important example because you want to try to save yourself some time, because where we're headed with this is we're going to have to do a quadratic formula. Now, there's a method in which you can make an assumption to avoid the quadratic formula, but you need to double check yourself once you get through it. So what we're going to do here in order to avoid trying to do a quadratic formula is we are going to assume that 2x is going to be far less than 0.10. So in other words, we're going to assume that 2x is a very, very small number. And if 2x is a very, very small number, when we add that small number to 0.10, it's going to just equal 0.10 with the sake of rounding in significant figures. So what we're really doing here is assuming that 2x is going to drop out relative to that large number that it's being added to. Okay? And this is generally a safe assumption, but you always go back and check it. Once we solve for x, we need to then take 2x and see if it really is small enough that it's going to be considered insignificant in comparison to the 0.1 there. So what we do when we simplify this then is it makes a much cleaner multiplication that we can solve. So now we say it's going to be 3.9 times 10 to the minus 11th equals x times 0.01. Now, where did 0.1 come from? Well, I did the squaring, okay? So if 2x drops out and then you take 0.1 and you square it, you're going to get that value. So then you can simply divide through by 0.01, 0.01. And so x is going to be 3.9 times 10 to the negative 9th. All right, so now that we have x, we should compare this quickly to 2x. So if I take this times 2, if I take x times 2, then what I end up with here is going to be 7.8 times 10 to the minus 9th. And this value is certainly small enough that in comparison to 0.1, it would be insignificant. So if I took 0.1 and then subtracted 7.8 times 10 to the minus 9th, so keeping in mind that there are 8 zeros in front of that 7, 8 there, that's such a small number that it's not going to have any reasonable effect. So we're okay with making this general assumption that we did here, and we can proceed forward. All right. So we have our value for x, and now what we're going to do is utilize that. Okay. Now keep in mind that when we solve this in KSP equilibrium terms, this is in molarity right now. All right. So we were looking for grams per liter here. So with grams per liter, what we would need to do is take the molarity, which is 3.9 times 10 to the minus 9th, okay, and that's moles per liter. And we're going to use the molar mass. Now the hint for that we needed to do that is that they give you this right here, right? So the reason we would need that is that we have to go ahead and use the molecular formula. So if you were to do that, it's 1 calcium and 2 of the fluorines. That comes out to approximately 78 grams per mole. All right, now when you're doing this, the moles are going to cancel and you're going to get grams per liter, and that's what we're looking for. So let's finalize this. If you multiply 3.9 times 10 to the minus 9th by 78, and you run that through your calculator, you're going to end up getting 2.9 times 10 to the minus 7th, and that's grams per liter. Okay, so that's the answer. Now remember what we said. Look at that answer, 2.9 times 10 to the minus 7th grams per liter. We said if it's 2.9 times 10 to the minus 7th grams per liter, then this is the correct answer. So the answer here would be C, because we started at this and then we accounted for the common ion effect right here, and we found that it has been decreased to this. This is the solubility as it sits right here. So it hasn't decreased it by this amount. This is the new amount. This is the new value here in grams per liter. So C is the correct answer, and that is how you would solve a common ion effect like we discussed earlier. All right, so that about wraps everything up for us, and hopefully you found this informative in terms of KSP and dilutions and concentrations, and we will see everybody in the future lectures as we prepare for more topics. Thanks a lot.